If you could travel at the speed of light, would time really stop for you? This question has become one of the most profound puzzles in physics, sparking debates that bridge science and philosophy. Time seems so absolute in our daily lives, ticking steadily forward no matter what we do. But relativity tells us that time is not universal. It bends, slows, and stretches depending on motion and gravity. So, if light itself represents the ultimate speed limit of the cosmos, what happens to time when you reach that threshold? Does it grind to a halt, or does it become something so unrecognizable that our human minds can't even truly grasp it? The speed of light, 299,792 kilometers per second in a vacuum, is not just an impressive number. It is woven into the very foundation of the universe. Unlike other speeds, which can be surpassed or varied depending on force and mass, the speed of light represents a cosmic boundary, an ultimate ceiling that no object with mass can ever break through. But why is this speed so special? To answer that, we must dive into the interplay between space, time, and the laws of physics themselves. Light speed isn't an arbitrary value plucked out of nature. It is the result of the fabric of reality and the rules governing how information and energy move through it. First, consider how speeds usually work in our everyday world. A car can move faster if you add more fuel and horsepower. A jet can go faster still with the right engines and aerodynamics. Rockets push the boundary even further by burning tremendous amounts of propellant. But as you move closer to the speed of light, physics introduces a resistance that no amount of fuel can overcome. Mass, energy, and time all interact in such a way that approaching light speed becomes increasingly difficult until the final step, reaching the exact speed of light, becomes impossible for anything that has mass. The number 299,792 kilometers per second is not negotiable. It is built into the very equations that describe electromagnetism, relativity, and causality. It is the one constant all observers, no matter how fast they are moving themselves, will agree upon. This universality is what makes light speed so extraordinary. In 1865, James Clerk Maxwell's equations showed that electromagnetic waves, including light, always move at this constant velocity in a vacuum. Decades later, Einstein took this result and used it as the foundation for his theory of special relativity. Unlike sound, which depends on the medium through which it travels, light speed is unaffected by whether the source is moving toward you or away from you. If you shine a flashlight from a spaceship moving at half the speed of light, the beam still travels at light speed relative to you and relative to anyone else observing it. This strange rule, that the speed of light is invariant, forces the universe to bend space and time themselves to make the math work. Think about what this means. The laws of addition that we apply to everyday speeds break down at these extremes. If a car is moving at 100 kilometers per hour and fires a ball forward at 10 kilometers per hour, the ball's speed relative to the ground is 110 kilometers per hour. That's simple. But if a spaceship is moving at half the speed of light and turns on a headlight, you do not add those speeds together. The light beam does not move at 1.5 times the speed of light. Instead, it still moves at the same constant speed, and instead, time and space themselves warp around the event to preserve the rule. This peculiar fact is one of the deepest insights science has ever revealed. Another reason light speed is considered the universal limit is because it is not just the speed of photons, it is the speed at which information can travel. In physics, information is bound by causality. Effects cannot precede causes, and nothing can influence something else faster than light can move between them. If signals could travel faster than light, it would be possible to break the cause and effect structure of the universe, leading to paradoxes like receiving a message before it was ever sent. Light speed protects the logical consistency of reality itself. In essence, it is not just a physical barrier, but also a safeguard against contradictions in time. Now, let's look at the role energy plays in this limit. As an object moves faster and faster, its relativistic mass increases. In simple terms, the faster it goes, the more energy is required to push it further. At everyday speeds, this effect is negligible, but as you approach light speed, the amount of energy required skyrockets. Near 99.999% of the speed of light, the energy demands become astronomical. At 100%, they become infinite. Since infinite energy is impossible in our universe, this makes the speed of light unreachable for anything with mass. Photons are exempt because they are massless, and that is why they can move at this extraordinary speed without being crushed by infinite energy requirements. Light speed also represents the fastest possible way for the universe to exchange information about events. When a star explodes millions of light years away, the very first hint we receive of that event is the light that races across space to reach our eyes. Nothing else, no physical signal, no particle with mass, can beat it. Gravitational waves, which ripple through space-time itself, also travel at the speed of light. This reinforces the idea that light speed is not about photons alone. It is the maximum velocity that anything, including the rippling geometry of the universe itself, can achieve. One of the most fascinating aspects of this cosmic speed limit is how it connects seemingly unrelated aspects of physics. The same value governs how light waves travel, how time dilates at high velocities, and how space contracts for fast-moving objects. It is the glue that ties together relativity, electromagnetism, and causality into a single coherent system. Without this invariant limit, the universe would not behave in the stable, logical way it does. Imagine a reality where information could propagate at arbitrary speeds. Particles could send signals into their own past, chains of cause and effect would break, and the structure of physics would collapse. The speed of light prevents such chaos, enforcing a consistent and orderly universe. The reason the speed of light is such a profound cosmic boundary leads us directly into the work of Albert Einstein. In 1905, he published his groundbreaking theory of special relativity, a framework that forever changed our understanding of space and time. Up until then, most people, including scientists, believed that time was absolute. A second was a second everywhere, ticking uniformly throughout the universe. But Einstein revealed that this intuition was flawed. Instead, he showed that time is not fixed at all. It is elastic, bending and stretching, depending on your speed and your frame of reference. The faster you move through space, the slower time appears to pass for you. This idea sounds almost like science fiction, yet it is a direct consequence of light's unchanging speed. Remember, in the previous discussion, we learned that light always moves at 299,792 kilometers per second, regardless of who is measuring it. If that rule is to remain true in every situation, something else has to give way. What gives is the flow of time and the structure of space. These two concepts, once thought of as independent, become intertwined into a single fabric that Einstein called space-time. If space changes to keep light speed constant, then time must also change. This is the revolutionary insight of special relativity. To understand it more deeply, imagine two observers, one standing still on Earth and the other moving rapidly in a spaceship. Both are carrying clocks. According to Einstein's equations, the clock in the spaceship will tick more slowly compared to the one on Earth, at least from the perspective of the person standing still. This isn't an illusion or a trick of perception. It's a real effect built into the laws of the universe. For the person on the spaceship, time feels perfectly normal. Seconds tick by, just as they always do. But for the stationary observer, the traveler's seconds stretch out longer, as though time itself has slowed down. This effect is known as time dilation, and it lies at the very heart of relativity. The faster you go, the more extreme the dilation becomes. At everyday speeds, the effect is so tiny that you'll never notice it. But as you approach a significant fraction of the speed of light, the difference grows dramatic. At 90% the speed of light, time for the traveler might slow to about half the rate of time experienced by someone at rest. At 99.9%, the difference becomes staggering. Push closer and closer to light speed, and the moving clock ticks slower and slower, creeping toward a standstill from the perspective of the outside observer. What's truly astonishing is that this slowing of time isn't just theoretical. It has been measured and confirmed. Particles moving at relativistic speeds inside accelerators decay more slowly than they would at rest. Astronauts aboard the International Space Station, moving at thousands of kilometers per hour, actually age infinitesimally less than people on Earth. GPS satellites, which orbit at high speeds and experience weaker gravity, must have their clocks corrected to account for relativistic effects. Special relativity isn't an abstract theory. It is a living reality that modern technology depends on. And yet, Einstein's insight went even further. He showed that not only does time dilate, but distances also contract. For someone moving at high speeds, the length of objects in the direction of travel appears shortened. This phenomenon, called length contraction, pairs with time dilation to preserve the speed of light. Both effects work hand in hand to ensure that no matter how fast you move, light's velocity remains constant to you. Space shrinks, time slows, but the rules of physics remain perfectly consistent. Einstein's relativity is not merely a set of equations, it is a complete reimagining of reality. It tells us that space and time are not rigid, separate entities, but flexible and deeply connected. They form a stage on which the universe plays out, and that stage bends under the influence of motion and energy. This idea was shocking in Einstein's time and continues to challenge our intuition today. After all, we live our daily lives assuming that time is uniform, but relativity reveals that the universe operates on a much stranger, more malleable set of rules. At its core, the theory teaches us that time depends on perspective. There is no single, universal clock ticking across the cosmos. Each observer carries their own time, tied to their motion. This relativity of simultaneity, the fact that different observers can disagree on whether events happened at the same time, upends the idea of absolute truth in physics. The concept of now becomes slippery, shifting depending on your speed and position. What seems like a single shared reality fractures into countless individual timelines, all stitched together by the speed of light. In tying all of this back to our original question, whether time stops at light speed, Einstein laid the foundation. His equations showed that the faster you move, the slower time becomes relative to others. Push this logic all the way to the ultimate limit, and the mathematics suggests that time would halt entirely at the speed of light. But as we'll soon discover, while the equations point in that direction, the reality is more complicated. For now, what matters is this. Relativity tells us that motion and time are inseparably linked. And that link is why the speed of light is not just special, but central to the very nature of existence. Einstein's revelation that time is not absolute naturally leads us into one of the most striking consequences of his theory, time dilation. If relativity tells us that motion bends the flow of time, then the question becomes, how exactly does this bending manifest? The simplest way to understand it is to think about clocks, those steady tickers we rely on to measure the passing of moments. According to relativity, if you set two identical clocks side by side and then send one racing off at a significant fraction of the speed of light, the traveling clock will tick more slowly, compared to the one left behind. When the traveller eventually returns, the two clocks will no longer agree. The moving clock will show less time elapsed, as though it has lived through fewer moments. This effect may sound impossible at first, because our everyday intuition insists that time is universal. A second feels like a second no matter where you are or what you are doing. But relativity dismantles this assumption. The speed of light's constancy forces the universe to adjust in other ways, and the adjustment comes in the form of stretched time. From the perspective of the moving clock, nothing unusual happens. It ticks normally, seconds feel normal, and the traveller notices no difference. But for the stationary observer watching that clock zoom past, the ticks come slower, the seconds are stretched, and the passage of time appears sluggish. The beauty of this idea is that both perspectives are correct. Time is not lying to either observer. It simply runs differently depending on the frame of reference. To picture it in a more grounded way, think of light as the ultimate cosmic referee. Since its speed cannot change, the universe compensates by altering the pace of time. This ensures that no matter who measures the speed of light, the result is always the same. Time dilation is the mechanism that balances the equation. It's as though time itself is pliable, slowing down for fast-moving objects to preserve the cosmic rulebook. The result is a universe where time doesn't march forward with a single beat, but instead pulses differently for every traveller depending on their speed. This effect is not confined to thought experiments. It has been observed countless times. Particles like muons, which naturally decay within millionths of a second, survive much longer when accelerated close to the speed of light in particle accelerators. From their own perspective, they decay on schedule. But from the perspective of scientists watching them, their clocks have slowed down, giving them extended lifespans. Similarly, astronauts orbiting Earth at high velocities experience slightly less passage of time than those of us on the ground. The difference may be fractions of a second over months, but it is measurable, and modern technology like GPS relies on correcting for this effect. Without accounting for time dilation, the entire navigation system would drift off course. What makes time dilation so fascinating is that it does not require exotic circumstances to exist. It's happening all the time, everywhere. You are already moving relative to countless other objects in the universe, which means your personal timeline is unique to you. Of course, at the speeds we typically experience, the differences are negligible, but in the vast stretches of space, where near-light speeds can be achieved, these differences become dramatic. A traveller moving fast enough could experience just a few years, while centuries pass for everyone else back home. This brings us back to the link between relativity and the idea of time stopping at the speed of light. Time dilation shows us the gradual pathway toward that extreme. At modest speeds, the effect is almost invisible. At higher speeds, it becomes noticeable. And as you approach the speed of light, the slowdown of time becomes so extreme that it approaches zero. The moving clock ticks more and more slowly, asymptotically approaching stillness. It is this relentless slowing that gives rise to the tantalizing idea that time could stop altogether if light speed were ever reached. Time dilation is, in essence, a reminder that time is not an independent backdrop against which the universe plays out. Instead, it is dynamic, flexible, and deeply intertwined with motion. Every moving clock tells its own story, and no two stories are ever exactly the same. This realization shatters the illusion of a single universal time, showing instead a universe where each path through space-time creates its own rhythm. And it is within that rhythm that the great mystery of light speed and the possibility of time stopping begins to unfold. Time dilation sets the stage for one of the most subtle but important distinctions in all of physics, the difference between traveling near the speed of light and actually reaching it. At first glance, it might seem like there's not much difference. After all, if you're traveling at 99.999% the speed of light, aren't you essentially moving at light speed? Doesn't time dilation already slow things down to almost nothing? While it's true that the effects become extreme at these velocities, the difference between almost and exactly is not just a small gap. It's a gulf that separates the possible from the impossible. Understanding this difference is key to answering whether time can ever truly stop. Let's begin with the case of approaching light speed. As an object with mass accelerates faster and faster, its time dilation increases. To outside observers, its internal clock ticks more slowly. At 90% of light speed, time dilation is noticeable, but still within a realm we can imagine. At 99%, the effect becomes striking. Seconds for the traveler might be minutes for those at rest. Push it further to 99.999%, and the dilation becomes so extreme that what feels like a few hours or days aboard a spaceship might translate into centuries or millennia for those back home. The mathematics tells us that as velocity inches closer to light speed, time for the traveler gets squeezed into smaller and smaller slices, nearly vanishing when compared to the outside world. But here lies the crucial difference. Nearly vanishing is not the same as gone. No matter how close you get, if you are still below light speed, even by the tiniest fraction, time continues to move forward for you, however slowly. Your heart still beats, your neurons still fire, your atoms still vibrate. The outside world might see these processes stretched into near stillness, but from your own perspective, life flows on as usual. The key is that time never actually hits zero. Instead, it approaches zero in a kind of asymptotic dance, always nearing but never reaching. Now consider the leap from almost to exactly. If you could somehow accelerate from 99.999% to 100%, relativity says the equations break. To move at the precise speed of light, your experience of time would no longer just slow. It would disappear entirely. Proper time, the personal measure of duration along your journey, collapses to nothing. From the outside perspective, your clock would be frozen, ticking not at all. And from your own perspective, if such a thing were possible, your entire journey, whether across a room or across the galaxy, would occur in no time at all. You would experience departure and arrival as the same moment, with no passage of time between. The problem is that this leap cannot happen for anything with mass. Approaching light speed is possible in principle, although unimaginably difficult in practice, because the energy required to accelerate keeps growing. But the final step to reach the exact speed of light is blocked by a wall of infinity. To push a massive object all the way to light speed would demand infinite energy, which the universe does not provide. This means the difference between almost and exactly isn't just a matter of degree, it's a matter of possibility versus impossibility. It is like running toward the horizon. No matter how fast you go, you never truly arrive. Another way to see the difference is by thinking about perspective. At near light speeds, a traveler might feel like time is passing normally for them, while the outside world races by at incredible speeds. They still have an experience of duration. They can eat meals, count seconds, and live through events. But if they were somehow able to actually reach the speed of light, that experience itself would vanish. There would be no meals, no seconds, no sense of before and after. Time as a concept would lose its meaning. For a photon, which is massless and always moves at light speed, this is the reality. It doesn't experience time at all. From emission to absorption, it has no sense of duration. It is timeless. This distinction also matters when we think about physics experiments. In particle accelerators, we can push electrons and other subatomic particles to velocities incredibly close to light speed. We observe their lifetimes stretch. their decay rates slow, exactly as relativity predicts. But even at these mind-boggling speeds, we never witness time stopping completely. The particles eventually decay. Their internal processes continue, albeit slowed relative to our frame. We can verify the approach to timelessness, but never the arrival. That final state belongs exclusively to particles like photons, which are born into it by virtue of having no mass. It's tempting to think of near-light travel as practically the same as light speed, but the truth is more profound. Near-light speeds show us the stretching, bending and warping of time in ways that still allow us to anchor ourselves to some sense of passage. Light speed, in contrast, strips away that anchor entirely. It is not simply slower, it is qualitatively different. Time doesn't just crawl, it ceases to exist for the traveller. That is the razor's edge that separates the two. The consequences of this are staggering when we think about human experience. Imagine a spaceship that could cruise at 99.9999% the speed of light. The crew inside might live out a normal few years of their lives, while tens of thousands of years unfold outside. Humanity might rise and fall in the span of their voyage, while they barely notice. Yet they would still age, still breathe, still experience time. Now contrast that with light speed itself. If it were somehow achievable, the very act of living through moments would vanish. There would be no journey, only instantaneous departure and arrival, collapsed into one timeless event. We've now arrived at perhaps the most fascinating perspective of all, that of the photon itself. While we've spent time discussing how massive objects slow down as they approach light speed, photons are born into a reality where they don't just approach. It is their natural state. They are massless, and because of this, they always travel at exactly the speed of light. For them, there is no acceleration, no gradual stretching of time, no struggle against infinite energy. They simply exist at light speed from the moment they come into being. And this unique status raises a remarkable implication. Photons do not experience time at all. To understand this, imagine a photon being emitted by a star. It bursts forth from the chaotic surface, racing outward into the cosmos at 299,792 kilometers per second. That photon might travel for 8 minutes before reaching Earth, or it might journey across interstellar space for thousands, even millions of years. From our perspective, that is an enormous span of time. To us, the photon is a patient traveller, carrying information from the distant past. But from the photon's point of view, if such a perspective could exist, there is no waiting, no passage, no duration. The moment of emission and the moment of absorption collapse into the same instant. This is where things get strange. We humans think of time as a fundamental backdrop against which all events occur. But for the photon, that backdrop vanishes. Proper time, the internal measure of duration along a path through space-time, is zero for anything moving at light speed. That means, as far as the photon is concerned, there is no between. There is no journey, no aging, no sequence of events. It simply exists at one location, and then at another, with nothing in between. For light, the universe is timeless. Think about what this really implies. A photon that leaves a star in a distant galaxy 5 billion years ago, from our perspective, has travelled across vast gulfs of space and time. It has waited billions of years before arriving at your eye or at the lens of a telescope. But from its own perspective, there was no wait at all. Emission and absorption are a single, instantaneous event. The photon has no memory of travel, because for it, travel does not exist. Time itself does not unfold. This is not just abstract speculation. It is built into the very mathematics of relativity. When an object moves at light speed, its proper time shrinks to zero. That's why photons don't decay the way other particles do. They don't have a timeline along which to age. They exist as carriers of energy and information, but not as participants in the flow of time. In this sense, light is fundamentally different from matter. Where matter experiences time as a continuous river, photons skip the river entirely. It's also worth noting that this timelessness is why photons are perfect messengers of the universe's history. They don't get older along the way. They don't erode or fade from the passage of time. A photon that began its journey billions of years ago arrives as fresh and intact as the moment it was born. This is why we can see the light of ancient stars and galaxies, why telescopes like Hubble and James Webb can peer into the distant past. Light doesn't just illuminate the universe, it preserves its history. Of course, we must be careful when speaking about what a photon experiences. Experience, as we know it, requires time, a sequence of moments, a before and after. A photon has none of that. It doesn't perceive, it doesn't age, it doesn't remember. To talk about its perspective is really to stretch language to the edge of metaphor. Still, the concept is powerful because it highlights how radically different light is from matter. It reminds us that relativity is not just a set of abstract equations, but a description of realities that defy human intuition. For us, the idea of timeless existence is almost incomprehensible. Everything about our lives is structured around the ticking of time, our growth, our thoughts, our movement from moment to moment. To imagine a state where time does not exist at all is to step outside the boundaries of human experience. And yet, photons live in that state effortlessly. Every beam of sunlight, every glimmer of starlight, every signal bouncing between satellites, all of it unfolds without the dimension of time. In the grand puzzle of whether time stops at the speed of light, photons provide a kind of answer. For them, time does not just slow, it vanishes. Not in theory, not as an unreachable limit, but as a lived reality. For light, there is no journey, only arrival. Emission and absorption are stitched together as one timeless event. And that makes photons not just carriers of illumination, but profound reminders that the universe is stranger than our deepest intuitions can grasp. If photons glide through the universe at light speed effortlessly, why can't we? Why can't a spaceship, with enough thrust and clever engineering, simply accelerate until it matches that same cosmic pace? The answer lies in what physicists call the energy barrier, a fundamental obstacle built into the very structure of relativity. For any object with mass, reaching light speed is not just difficult, it is impossible, because doing so would require an infinite amount of energy. To understand why, we need to look closely at how mass and energy interact when an object accelerates. In everyday life, accelerating an object feels straightforward. You push a toy car and it speeds up. You press the gas pedal and your vehicle picks up velocity. The harder you push, the faster it goes. There is no sense that something is resisting you in a mysterious way. But this intuition is limited to the low-speed world we inhabit. As soon as you start thinking about speeds that are a significant fraction of the speed of light, the rules change dramatically. Suddenly, an invisible resistance emerges, not friction, not drag, but a deep resistance embedded in the very fabric of space-time. Here's how it works. In Einstein's framework, mass and energy are two sides of the same coin. When you accelerate an object, you're not just increasing its speed, you're increasing its energy. As its energy grows, its resistance to further acceleration grows as well. From the perspective of someone watching, it's as if the object is becoming heavier and heavier the faster it goes. This is sometimes described as an increase in relativistic mass, though today physicists prefer to frame it in terms of energy directly. The key point is the same. The more you accelerate, the harder it becomes to accelerate further. At modest speeds, this effect is negligible. A car doubling its speed requires more fuel, but it's nothing extraordinary. Even for a jet or a rocket, the relationship between energy and speed feels manageable. But as you push an object closer to the speed of light, the demands escalate dramatically. At 10% of light speed, the increase in energy demand is noticeable, but still within the realm of imagination. At 90%, the energy required is staggering. At 99.9%, it's nearly incomprehensible. And as you approach 100%, the required energy doesn't just grow large, it shoots upward without limit, racing toward infinity. That final step is unattainable, because infinity is not something nature can provide. Think about this in terms of practical engineering. Suppose you had a spaceship with engines capable of unimaginable thrust. You could feed it all the fuel you want, even harness the power of entire stars. As you accelerate, the ship keeps getting closer to the speed of light, but each additional burst of energy moves you less and less forward in terms of percentage. The harder you push, the smaller the gain becomes. By the time you are within a hair's breadth of light speed, you could pour the energy of entire galaxies into the attempt and still fall short. The speedometer creeps closer and closer, but never touches that final mark. This energy barrier is not simply an inconvenience, it is a law of nature. It is built into the equations of special relativity in such a way that the speed of light acts like a vertical wall. Approaching it is possible, but climbing over it is not. That is why photons, being massless, get to live on the other side of the wall. They never had to climb it at all. For them, it's their natural state. But for anything with even the tiniest shred of mass, a grain of sand, a bacterium, or a human spacecraft, the wall is absolute. The concept of infinite energy is itself worth pausing on. Infinity is not just a lot. It is not like saying we'd need the output of 1 trillion suns. Infinity means there is no amount of energy, no number of stars, no manipulation of physics that could ever be enough. It is a signal that the very idea is forbidden, not just impractical. In physics, when you encounter an infinity in an equation, it usually points to a boundary where the laws themselves stop being applicable in the way we're trying to use them. That's what happens with light speed. The math tells us that as velocity approaches this limit, energy soars without bound. It is nature's way of saying, this is not possible for you. Interestingly, this infinite energy requirement has other consequences. For instance, it explains why particles in particle accelerators can never quite hit light speed, no matter how powerful the machines become. Electrons in the Large Hadron Collider or similar facilities are accelerated to 99.999999% of light speed. Their lifetimes stretch dramatically because of time dilation, and their energies become so immense that they smash apart other particles when they collide. But even in these extreme conditions, the electrons still remain shy of the final barrier. The machines can pump staggering amounts of energy into them, yet the speedometer always shows less than c. The wall of infinity holds firm. This also means that light speed is not a frontier waiting to be conquered, like the sound barrier was. In the early 20th century, many people assumed supersonic flight was impossible because the air resistance grew dangerously high as planes approached Mach 1. But once we engineered around those aerodynamic problems, the barrier was broken. Some might wonder if light speed is a similar case, just waiting for better technology. Relativity tells us it is not. The speed of light isn't an engineering problem. It's a structural limit of space-time. Unlike the sound barrier, it cannot be broken because it is not caused by environmental resistance. It is the ultimate rule of motion in our universe. Now, let's connect this back to the question of time. The infinite energy barrier is the reason humans, or any object with mass, can never actually test what happens to time at light speed. We can get closer and closer, watching time slow more and more, but we can never cross into the realm of zero time ourselves. For photons, that realm is normal. They live there. But for us, the wall of infinity keeps it forever out of reach. This divide between massless and massive particles is one of the clearest reminders that light occupies a special category in physics, a realm where timelessness and limitlessness converge. We've seen how the energy barrier makes light speed unreachable for any object with mass, but relativity doesn't just stop there. It also tells us what would happen mathematically if you kept pushing faster and faster toward that limit. Even though no massive traveler can cross the boundary, the equations themselves lay out a clear trend. Time doesn't stop suddenly like a switch being flipped, but instead approaches zero more and more closely as your speed inches toward light speed. This is where the math becomes a window into the invisible fabric of reality. Now, don't worry. We're not going to throw complicated formulas at you. Instead, let's unpack the idea behind them. In Einstein's special relativity, there's a factor that shows up when you compare time for someone who's moving to time for someone at rest. This factor grows larger the faster you go, and as it grows, it stretches the traveler's seconds into longer and longer slices when viewed from the outside. At everyday speeds, this stretching is so small you can ignore it. At higher speeds, it becomes measurable. And as you near light speed, the factor skyrockets, making those moving seconds appear almost frozen. The beauty of this is in the way the numbers behave. Relativity doesn't predict a sudden jump where time just cuts off. Instead, it paints a smooth curve. Imagine a graph where the horizontal axis is speed and the vertical axis is the flow of time. At low speeds, the line sits near the top, showing time flowing normally. As you speed up, the line starts to slope downward, showing time slowing. The closer you get to light speed, the more the line plunges downward, but it never quite hits the bottom. It hugs the axis, approaching zero without ever touching it. This mathematical behavior mirrors what we've already discussed. Time slows dramatically, but never truly stops unless you could actually reach the unattainable speed of light. This asymptotic approach, that smooth, endless nearing of zero, is what makes relativity so elegant and so frustrating at the same time. It gives us a roadmap that says, the faster you go, the less time you experience. But it also tells us that the final destination of timelessness is unreachable for anything with mass. The equations show us the direction, but also slam the door shut before we can cross the threshold. What's astonishing is that this mathematical prediction matches reality. Particle accelerators confirm it with subatomic particles, where decay times stretch exactly as the equations say they should. Astronauts experience minuscule but measurable differences in aging relative to people on Earth. GPS satellites run on clocks that tick slightly differently because of their speed. Everywhere we look, the predictions hold. Time really does stretch according to this curve, with no exceptions. The math is not just abstract theory, it is a precise description of how the universe operates. This also means we can use mathematics to make some incredible thought experiments. For example, if you were traveling at 99.9% of the speed of light, the equations would predict that your time runs about 20 times slower than someone at rest. At 99.9999%, the difference is even more staggering. Seconds for you could mean years outside. Push the numbers further, and you can see how your personal experience of a short journey could coincide with entire civilizations rising and falling back home. The closer you get to light speed, the more extreme these differences become. Yet no matter how far you push the numbers, the equations always stop just short of hitting absolute zero. This is where the contrast with photons becomes so fascinating. For them, the math gives a clean result. Proper time is zero. A photon doesn't have to creep toward timelessness. It lives there permanently. For us, the equations say proper time shrinks but never vanishes. That's why photons can serve as messengers from the early universe, carrying information billions of years without ever aging, while we remain bound to our slow, steady clocks. The mathematical breakdown also highlights why relativity is so radical compared to the physics that came before it. In Newton's world, time was absolute and unchanging. There was no graph sloping downward, no asymptote to approach. Everyone shared the same universal clock. Einstein shattered that view, replacing it with a dynamic, flexible framework where time is relative and malleable. The equations of relativity are not just tools for calculation. They are symbols of a new way of thinking about existence itself. So, what do the equations really say? They say that time is a function of motion. They say that speed and time are intertwined in a way that guarantees light speed is a singular state of timelessness, forever beyond the reach of the massive. They say that for us, time is never zero, but always something, no matter how small. And they say that photons, massless and eternal, are the only entities that truly live on the other side of the graph, where time itself no longer exists. This mathematical picture is what makes the question, does time stop at light speed, so profound? On paper, yes. If you could somehow be massless, if you could move at exactly light speed, then your proper time would be zero. But because of the infinite energy barrier, this solution exists only in the equations, not in the realm of possibility for us. What the math really shows is the boundary, a universe where time slows to a crawl as you approach the cosmic limit, but never freezes completely for anything bound by mass and energy. Up to this point, we've seen how relativity stretches time thinner and thinner as speed increases, and how photons live in a state where proper time is always zero. But this brings us face to face with one of the deepest questions of all. Does time actually stop at the speed of light, or does it simply become undefined? At first glance, it feels tempting to say yes, time stops. After all, the equations point to proper time shrinking towards zero, and for photons, that number is exactly zero. But the closer you look, the less straightforward the answer becomes. The truth lies not in simple stillness, but in a strange, undefined space where our familiar concepts of time break down. Let's start with what we know. For anything with mass, the rules are clear. Time never stops, it only slows relative to other observers. You can make it run so slowly that an entire human lifetime on your clock might correspond to thousands or millions of years outside, but it will always keep ticking. That steady, personal passage of time, your heartbeat, your thoughts, your moments, remains intact from your perspective, no matter how fast you go. Relativity tells us this flow cannot be erased as long as you have mass. So in this sense, time does not stop. It cannot. But photons are the exception, and that is where the paradox emerges. For them, the universe's equations say proper time is zero. That seems like a clean statement. Time has stopped. Yet the word stopped may not even apply here, because to stop something implies it existed in the first place and then halted. For photons, time never flowed at all. Their reality is not one of frozen moments, but of timelessness. The emission of the photon and its absorption are stitched together as if they are the same event, with no intervening passage of time in between. Saying that time stops for photons is more a shorthand for us to grasp something fundamentally alien. For them, time doesn't exist in the first place. This subtlety makes all the difference. To ask whether time stops at light speed is to apply human intuition to a domain where it no longer fits. Our language evolved in a world of minutes, hours, and days, measures of duration. But at light speed, duration itself disappears. The word stop suggests a frozen clock, but in reality, there is no clock at all. The flow of time becomes undefined, outside the framework we use to measure experience. Another way to think about this is through perspective. For us, observing from the outside, photons seem to have traveled across unimaginable distances over unimaginable spans of time. A photon from a distant galaxy may have crossed billions of years of cosmic history to arrive at our telescopes. From our vantage point, time has very much passed. But from the photon's perspective, if we dare to use that phrase, those billions of years don't exist. There was no interval between departure and arrival, only a single, timeless event. In this sense, time hasn't stopped for the photon. It was never a factor at all. This leads us to a profound realization. The question, does time stop, might not even be the right question to ask. For massive objects, the answer is no, because they can never reach the condition where time could vanish. For massless objects like photons, the answer isn't exactly yes, because stopping implies something that doesn't apply to a timeless entity. The real truth is that time becomes undefined at light speed, because time itself is a property that belongs only to objects with mass, energy, and a world line through space-time. Light does not have that kind of world line. It simply exists across space-time in a way that transcends our notions of before and after. This perspective also explains why the speed of light is such a cosmic boundary. It doesn't just mark the fastest velocity possible, it marks the dividing line between two fundamentally different regimes of existence. On one side, you have matter, bound by mass and energy, where time is always flowing, however slowly. On the other side, you have light, massless and timeless, existing outside the flow of moments altogether. The barrier is not only about energy, but about the very definition of time itself. When people ask if time stops at the speed of light, what they're really asking is whether time has an absolute endpoint. Relativity's answer is subtle. For us, bound by mass, the endpoint is forever out of reach. Time never truly stops. For light, time is not just stopped, it is irrelevant. This dual truth may feel unsatisfying because it resists our desire for a simple yes or no. But in many ways, that resistance is what makes the question so profound. It forces us to confront the limits of human intuition and the strangeness of the cosmos itself. In conclusion, does time actually stop at light speed? Not exactly. For us, it cannot. For light, it doesn't stop, but instead transcends the concept entirely. Time becomes undefined, irrelevant, non-existent, and it is in that undefined realm that the universe reminds us just how alien its deepest truths can be. From everything we've explored so far, one lesson stands out clearly. The passage of time is not universal. Instead, it depends on perspective. This becomes especially striking when we compare the experience of someone traveling near light speed with the experience of someone standing still and watching them. Both observers are correct in what they perceive, but their realities diverge so drastically that it almost feels like they're living in separate universes. This contrast between the traveler and the observer is one of the most mind-bending consequences of Einstein's relativity. Let's first place ourselves in the shoes of the traveler. Imagine you're aboard a spacecraft moving at 99.99% the speed of light. Inside, everything feels perfectly normal. Your heartbeat beats at its usual pace. Your thoughts flow naturally. The clocks on the ship tick second by second. You eat meals, sleep, and carry on life as though nothing extraordinary is happening. From your perspective, time has not slowed down at all. It feels exactly the same as it would sitting at home on Earth. You are in your own personal frame of reference, and within it, physics guarantees that everything behaves as expected. Now switch to the perspective of someone watching you from Earth. As they observe your ship racing through space, they notice something extraordinary. Your onboard clock doesn't tick at the same rate as theirs. It ticks more slowly. Your heartbeat, your speech, even your movements are stretched out. If they could watch you wave your hand, they'd see it happen in slow motion compared to their own hand waving in front of them. To them, it looks as though your entire life is unfolding in a stretched, slowed-down rhythm. And the faster you go, the more pronounced this effect becomes. At extreme speeds, what seems like a few hours for you could appear as decades or centuries passing for them. This contrast is not an illusion or a trick of perspective. It's not like the distortion we see in funhouse mirrors or the shift in sound from a Doppler effect. It's real, built into the fabric of space-time. Both viewpoints are valid and consistent within their own frames. The traveler genuinely experiences normal time, and the observer genuinely experiences slowed time for the traveler. The difference arises because relativity insists that time is not a single absolute flow. Instead, each observer has their own time, tied to their motion and their frame of reference. This leads to some startling consequences. Suppose you and your friend part ways, with you heading off on a near light-speed journey while they remain on Earth. From your perspective, the trip might only take a few years. You might read books, conduct experiments, and age normally as the voyage continues. But when you return home, you could find that decades, centuries, or even millennia have passed on Earth. Your friend may be long gone, civilizations may have changed, and history may have leapt forward far beyond your lifetime. You would have experienced a short, personal trip, but your observer experienced a vastly different passage of time. What's important here is that neither perspective is more true than the other. There isn't a universal master clock ticking behind the scenes that one of you is misreading. Both of you are living in realities that are equally valid, defined by your relative motion. This is why relativity is so radical. It tells us that time itself is not a fixed backdrop, but a flexible, relative phenomenon. For the traveler, life feels completely normal. For the observer, the traveler's life looks slowed down. And the universe allows both to be correct simultaneously. This split also highlights just how alien near-light travel would be for humans. We're so used to sharing a common experience of time that we can hardly imagine two people aging at drastically different rates. Yet relativity says this isn't just possible, it's inevitable at extreme speeds. It's not science fiction, but physics, confirmed by experiments with fast-moving particles and even by satellites orbiting Earth. The only difference is scale. For us, the effects are small at low speeds, but at near light speeds, they become cosmic in scope. Ultimately, the contrast between the traveler and the observer serves as a powerful reminder of relativity's central lesson. Time is not absolute. It flows differently depending on motion, and those differences can grow so vast that they fracture our very sense of reality. For the traveler, time remains ordinary, flowing second by second. For the observer, the traveler's time stretches almost into stillness. Both are correct, yet their truths diverge in ways that challenge everything we think we know about existence. The contrast between a traveler moving near light speed and an observer remaining behind reaches its most famous and thought-provoking illustration in what's known as the twin paradox. This scenario has become a cornerstone of relativity discussions because it captures the bizarre and counterintuitive way time behaves when different observers are in relative motion. It's a story of two siblings whose lives unfold along dramatically different timelines, not because of fate or choice, but because of physics itself. Here's how the paradox is usually framed. Imagine two identical twins on Earth. One stays at home, living a normal life, while the other boards a spaceship capable of traveling at a significant fraction of the speed of light. The traveling twin embarks on a journey across the cosmos, moving at extraordinary velocities, before eventually turning around and coming back. When the two twins reunite, something astonishing has happened. The twin who traveled is biologically younger than the one who stayed behind. They may have been born at the same instant, but relativity dictates that their experiences of time will not be the same. At first glance, this outcome sounds contradictory. After all, relativity insists that all motion is relative. From the perspective of the traveling twin, couldn't they argue that it was actually the sibling on Earth who was moving away, while they themselves were stationary? Shouldn't each twin see the other as aging more slowly? This is the root of the so-called paradox. It seems to suggest that relativity predicts two opposite outcomes at once. But when you look deeper, the resolution becomes clear, and in the process, it reveals just how strange time really is. The key lies in the fact that the twin situations are not perfectly symmetrical. The sibling on Earth remains in one frame of reference the whole time, at rest relative to the planet. The traveling twin, however, does not. At some point during their journey, they must decelerate, turn around, and accelerate back toward Earth. That change of direction breaks the symmetry. It means that the traveler's experience of space-time is different because they undergo acceleration, while the twin on Earth does not. This difference allows relativity to resolve the situation consistently. The traveling twin really does age less. To grasp how this works, let's explore it from both perspectives. From the Earthbound twin's point of view, the traveler's clock is always ticking more slowly due to time dilation. As the spaceship races away, the twin on Earth watches their siblings' seconds stretch out. When the ship turns around and returns, the same effect continues. By the time they meet again, the Earth twin has lived through more years than the traveler has. The math of relativity makes this outcome precise, with the difference depending on how fast and how long the trip was. From the traveler's point of view, life aboard the spaceship feels normal. Their heart beats at its usual rhythm, their meals and days pass just as they should. But when they look out toward Earth, they see their twin's clock running fast compared to their own during certain phases of the journey. The turning point, when they switch direction, is where the relativity of simultaneity comes into play. This concept, another strange prediction of relativity, says that different observers can disagree about whether events happen at the same time. Because of the acceleration during the turnaround, the traveler's perspective resets in a way that makes their siblings' timeline leap ahead. This resolves the paradox. Both views, though seemingly contradictory, fit together perfectly once you account for the relativity of simultaneity. The result is not just a curious thought experiment. It has real physical consequences. Experiments with subatomic particles, like muons created in the upper atmosphere, confirm the effect. Muons decay rapidly, yet when moving near light speed, they live much longer than they would at rest, just as relativity predicts. In laboratories, scientists have used particle accelerators to send these particles racing at relativistic speeds, and have consistently found that their clocks run slow compared to stationary ones. On a smaller scale, astronauts and satellites experience measurable time dilation too. Though the differences are tiny, fractions of a second, they're real, and they prove that the same physics applies universally. Now let's return to the human side of the paradox, because this is where the imagination really starts to stretch. Suppose one twin spends a year traveling at 99.999% of the speed of light before coming back. From their perspective, the trip might have taken only a year or two. But for the sibling on Earth, decades could have passed. Imagine the emotional shock of returning home to find your twin older, perhaps even elderly, while you remain young. Imagine stepping back onto your home planet only to discover that society has advanced, technology has leapt forward, and the world you left is now a memory. The twin paradox forces us to realize that time travel into the future is not only possible but unavoidable if near light speed travel could ever be achieved. It's not science fiction, it's physics. This scenario also highlights the role of proper time, the personal measure of time experienced along a traveler's path. The Earth twin accumulates more proper time because they remain at rest, while the traveling twin accumulates less because of their high-speed journey. Proper time is what makes the outcome unambiguous. The clocks are not lying, and the difference is not a trick of perspective. The twins genuinely live through different amounts of time. The twin paradox is resolved by relativity, but it leaves us with an unsettling truth. Time is not shared equally. It bends for those who move differently, and those bends can stretch across years, centuries, or even millennia. It tells us that time travel is not just possible in theory, but baked into the very laws of motion. And it reminds us that the universe, in all its elegance, is far stranger than the steady ticking clock we cling to in our daily lives. In our exploration of relativity so far, we've brushed against the idea of proper time, but now it's time to dive deeply into it. This concept is the backbone of understanding how time behaves for different observers, and it provides the clearest explanation of why photons live outside of time altogether. Proper time is one of those ideas that seems deceptively simple, yet it changes the way we think about existence itself. So what exactly is proper time? In plain terms, it is the time measured by an object's own internal clock as it moves along its path through space-time. Think of it as the personal diary of time experienced by that object. No matter how the object moves, whether it sits still, accelerates, or zips across the cosmos, proper time is the unique record of moments it lives through. For you and me, our proper time is the rhythm of our heartbeats, the ticking of our watches, the minutes and hours we actually feel. It's not about what anyone else sees. It's about the time that belongs uniquely to us. Now, here's where relativity makes things fascinating. Proper time is not the same for everyone. Two people moving differently can accumulate different amounts of proper time between the same pair of events. This is exactly what we saw in the twin paradox. The stay-at-home twin had more proper time, while the traveler had less. Both had their own diaries, their own internal timelines, and when they compared notes at the end, those diaries didn't match. This mismatch is not an illusion or a trick. It is the real consequence of motion through space-time. Why does this happen? Because proper time is shaped by how you move relative to the speed of light. The faster you travel, the less proper time accumulates for you compared to someone who remains at rest. At modest speeds, the difference is negligible, but as your velocity approaches light speed, your proper time shrinks more and more. In other words, your personal diary begins to have fewer pages compared to someone else's. What feels like a short trip to you might correspond to a long saga in someone else's proper time. Now extend this logic to the ultimate limit, the speed of light itself. If you could somehow travel at exactly that speed, which, as we know, is impossible for anything with mass, your proper time would collapse to zero. That means your diary of moments would contain no entries at all. From the perspective of proper time, the entire journey, whether across a room or across 1 billion light years, would take no time at all. There would be no duration to record. For photons, this isn't a thought experiment. It's reality. They don't have diaries because they don't accumulate time. For them, emission and absorption are stitched together as a single, timeless event. This is why proper time is such a powerful concept. It not only explains time dilation in everyday terms, it also clarifies what timelessness at light speed really means. It's not that clocks freeze in some cosmic slow motion, it's that clocks don't tick at all. There is no internal passage of moments to mark. Time doesn't just slow down, it disappears from the perspective of the traveller at light speed. But notice how important the distinction is between approaching and reaching. For an object with mass, proper time can get very small, but it never actually vanishes. A spaceship moving at 99.999% of light speed might experience just a few minutes while centuries pass outside. The crew's diary would be short, but it would still exist. Only at the unreachable limit of light speed does proper time drop to zero. That boundary marks the line between the world of matter, where time always flows, and the world of light, where time is non-existent. Proper time also helps us understand why the universe seems so coherent despite these strange effects. Each object, each person, each particle moves through space-time with its own diary of time. Those diaries may not match when compared, but each one is internally consistent. You never feel your own time stretch or shrink. It always flows normally for you. It's only when you compare your diary with someone else's that the differences emerge. This relativity of time is what gives the universe its paradoxical flavor. Everyone is right, but no one shares the same truth. To see how profound this really is, think about light from distant stars. Some photons have traveled across the universe for billions of years, crossing unimaginable gulfs of time and space. Yet in terms of proper time, their diaries are empty. For them, there was no journey, no passage. They left and they arrived, with nothing in between. That's why light serves as such a stark reminder of the strange boundary at the heart of physics. For matter, proper time stretches and shrinks, but never dies. For light, proper time is simply zero, always and forever. So, does time stop at light speed? Proper time tells us that the question itself is tricky. For massive objects, it never stops. It only slows, always leaving some diary of moments behind. For photons, time doesn't stop. It's never started. Proper time vanishes into nothingness, erasing the very possibility of a timeline. And in that vanishing lies the sharpest distinction between us and the particles of light that carry the universe's history across the stars. So far, we've built up a picture of how time bends, stretches, and even disappears as you push closer and closer to light speed. We've seen that photons live in a realm of timelessness, while matter is bound by proper time. But there's a pressing question that naturally follows. If relativity suggests that time would vanish entirely at light speed, why don't we just test it directly? Why not build a spaceship, accelerate it to the speed of light, and see if time really does stop? The answer, unfortunately, is that nature has placed an unbreakable barrier in front of us. No physical object with mass can ever actually reach light speed. This is not simply a limitation of technology. It's a fundamental law of physics itself. Let's revisit the reason. Every object with mass requires energy to accelerate. At low speeds, this is straightforward. Give it a push, and it moves faster. But as the object's velocity increases, the demands for energy grow disproportionately. The closer you get to the speed of light, the harder it becomes to squeeze out even the tiniest increase in speed. Imagine running toward a finish line that keeps moving further away the faster you go. You never get closer in a meaningful way. By the time you're at 99.9% of light speed, you'd need absurd amounts of energy to push just a little faster. At 99.9999%, the energy requirement is astronomical. And to hit 100%, you'd need infinite energy, infinite fuel, infinite resources. a demand that is simply impossible to meet within our universe. This infinite energy barrier isn't just a mathematical inconvenience. It's a deep truth about reality. It reflects the way space and time are structured. Light speed isn't like the sound barrier, which once seemed insurmountable but was eventually broken with clever engineering. The sound barrier was tied to air resistance and shock waves, phenomena within the atmosphere. Once those were managed, jets easily flew supersonic. The light speed barrier is not external. It's woven into the equations of space-time itself. No clever trick or technological leap can rewrite that. To try is like trying to divide by zero. It's not hard, it's meaningless. This is why no experiment has ever shown a massive object reaching light speed. Even in particle accelerators, where scientists hurl electrons and protons to mind-boggling velocities, the rule holds. These particles can get astonishingly close to light speed, 99.999999% in some cases, but never actually touch it. Scientists can pump more and more energy into them, and what happens is that the particles gain more mass energy, not more speed. Their kinetic energy increases, their collisions become more violent, but their velocity asymptotically approaches light speed without ever reaching it. Nature enforces the barrier with absolute rigor. What does this mean for our question about time stopping? It means we can never directly measure or experience the effect ourselves. We can't ride in a ship, look at our watch, and confirm that the hands have stopped moving at light speed. The best we can do is infer, extrapolate, and apply the mathematics of relativity. That's why the question remains so tantalizing. It's a boundary case, a prediction of the equations that cannot be physically tested for anything with mass. We can observe the slowing of time as we approach the barrier, but the final leap into timelessness is forever off limits to us. It's important to understand how unusual this is in science. Normally, when equations predict something, we can find a way to test it, directly or indirectly, through experiments or observations. But in this case, the very laws of physics prevent us from testing the ultimate prediction. This doesn't mean the prediction is wrong. In fact, relativity has been tested in every way that is possible, and it has passed with perfect accuracy. From particle accelerators to satellites, every experiment confirms the theory's validity. It's just that the one case, actual light speed for a massive traveler, sits forever outside our experimental reach. Some might wonder, could the future hold a loophole? Could advanced civilizations, with technologies we can't imagine, somehow find a way to bypass the barrier? Science fiction often plays with ideas like warp drives, wormholes, or shortcuts through higher dimensions. These are fun and even inspiring, but they're not the same as directly reaching light speed. Warp drives, for example, don't accelerate a ship to light speed. They manipulate space-time around the ship to move faster than light relative to the outside. Wormholes, if they exist, don't rely on breaking the light speed barrier. They create shortcuts through the fabric of space itself. None of these violate relativity's statement that no massive object can travel through space at light speed. They're attempts to go around the rule, not through it. This impossibility also ties back to the photon's unique status. Photons have no mass, so they're not bound by the same constraints. They don't need energy to reach light speed. They exist at it naturally. That's why they can live in a timeless reality that we can never share. For them, proper time is zero by definition. For us, tied to mass, proper time always exists, no matter how small, because the barrier prevents us from stepping into their world. The impossibility of testing light speed directly isn't just an experimental limitation. It's the very reason why matter and light inhabit such fundamentally different categories of existence. So why can't we test time stopping at light speed? Because time stopping at light speed belongs to a realm we can never enter. The laws of relativity are like the rules of a game that set clear boundaries. Photons play by one set of rules. we play by another. For us, the edge of light speed is a horizon we can approach but never cross. The closer we get, the stranger time becomes, stretching into near stillness. But the final truth, the disappearance of time itself, remains visible only through the eyes of light. If we can never directly test what happens at the exact speed of light, the next best thing is to study objects that come extraordinarily close. And that's exactly what physicists do using some of the most powerful machines humanity has ever built: particle accelerators. These colossal devices allow us to fling subatomic particles such as electrons, protons, and muons to velocities unimaginably close to light speed. In doing so, they become our laboratories for relativity, letting us witness how time behaves when pushed to extremes. One of the most striking examples comes from the behavior of muons. Muons are particles similar to electrons, but they are unstable, with an average lifetime of only about 2/10,000ths of a second before they decay into lighter particles. Under normal conditions, muons vanish almost instantly. But in particle accelerators, when muons are accelerated to near light speeds, their lifetimes increase dramatically. Instead of surviving for microseconds, they persist for milliseconds or even longer from our perspective. In other words, the faster they move, the slower their internal clocks tick relative to us. This is not theoretical, it's measured, tested, and confirmed with astonishing precision. Electrons also provide a clear example. At low speeds, their behavior is predictable and well understood. But when accelerated to 99.999999% of light speed in accelerators like CERN's Large Hadron Collider or Fermilab's Tevatron, electrons and other particles begin to exhibit the full strangeness of relativity. They don't suddenly smash through the light speed barrier. Instead, they asymptotically approach it, requiring more and more energy for smaller and smaller gains in speed. Along the way, their relativistic effects become undeniable. Time dilation stretches their decay times, their mass energy skyrockets, and their collisions release energies high enough to reveal the hidden structure of matter itself. It's here that the predictions of relativity align perfectly with experimental data. Every time scientists measure the extended lifetimes of these fast-moving particles, they confirm the equations that describe time dilation. The math says that proper time shrinks as velocity increases, and the particles obey flawlessly. If muons at rest live for 2/10,000ths of a second, muons traveling near light speed can live hundreds of times longer from our perspective. This stretching of lifespans is not just a curiosity. It is a direct, physical demonstration of time dilation in action. What's even more fascinating is that, from the particle's point of view, nothing has changed. A muon traveling at near light speed doesn't feel slowed down. It still decays in 2/millionths of a second by its own clock. Its proper time remains normal. But to us, watching from the outside, its internal processes unfold more slowly. This is the same traveler-observer contrast we explored earlier, but now played out at the tiniest scales of reality. The muon lives a short, normal life in its own timeline, while in ours it becomes strangely long-lived, racing across entire laboratories before it decays. These results are more than academic. They have practical consequences. For example, cosmic rays constantly bombard Earth's atmosphere, creating showers of muons. If relativity weren't real, those muons would decay long before they ever reached the surface. But because their near-light speeds stretch their lifetimes, they make it all the way down, where detectors can capture them. Every muon that hits a detector on Earth is a living proof that time dilation is not just theory, but the way the universe actually works. Particle accelerators also reveal another key truth. The closer you push to light speed, the less difference extra energy makes in terms of speed. Electrons in accelerators don't move noticeably faster than cosmic rays that have been flying through space for billions of years. Both are essentially at light speed already, yet not quite. This asymptotic behavior perfectly matches relativity's prediction that light speed is a wall you can never cross. The accelerators confirm that no matter how much energy you pour in, particles with mass never reach that final barrier. What we learn from these experiments is twofold. First, relativity is confirmed over and over again, with no exceptions. The equations describing time dilation, length contraction, and energy growth are not just abstract, they are mirrored in reality to astonishing accuracy. Second, the universe itself enforces the rules. Even at the bleeding edge of energy, particles respect the light speed barrier. They let us peer close to the threshold, close enough to see time nearly vanish, but never to watch it disappear entirely. This is why particle accelerators are often described as windows into the relativistic world. They don't just smash particles together, they also let us test how time behaves under extreme conditions. Without them, relativity might remain a theory supported by indirect observations. With them, it becomes a tangible, measurable reality. Every elongated muon lifetime, every stretched clock, every stubborn refusal to break the light speed barrier tells us the same thing. Einstein was right. And perhaps most intriguingly, these machines give us a glimpse of what it would mean if humans could ever experience near-light travel. The muons are like tiny test travelers, carrying clocks that slow down compared to ours. They remind us that, in principle, a human crew moving near light speed could experience a short, personal trip while centuries unfolded back on Earth. Particle accelerators show us that this isn't fantasy. It's the logical extension of the same physics we see at work in the lab. By now, we've seen how particle accelerators prove that time slows dramatically for matter racing close to light speed, and how photons exist forever in the realm we can't reach. This naturally leads us to the ultimate question: does time stop for light itself? The answer is subtle, because to even ask whether light experiences time is to impose human intuition onto something that exists outside of it. Light doesn't experience time the way matter does, not because it's frozen in a permanent pause, but because the very idea of time is meaningless for it. Let's start with the basics. Light always travels at 299,792 kilometers per second in a vacuum. It doesn't matter who measures it, or from what frame of reference. It is constant. For objects with mass, this speed is a limit, but for photons, it is their natural state. And because photons have no mass, they have no proper time. That means they don't accumulate duration the way you and I do. They don't carry diaries filled with moments. They don't have a before and after. From the instant a photon is emitted to the instant it is absorbed, no time passes for it at all. Imagine sunlight leaving the surface of the sun and traveling 8 minutes to Earth. For us, it's a clear delay. We wait those minutes before we feel the warmth or see the light. But for the photon itself, there was no delay. Emission and absorption were the same event. If you stretch that thought experiment across cosmic distances, the effect becomes even more astonishing. Light from a distant galaxy might take billions of years to reach our telescopes. To us, those photons are ancient messengers, carrying news from the deep past. But for the photons, there was no journey at all. They weren't alive for billions of years. They simply existed outside of time until they arrived. So, does time stop for light? The more accurate statement is that light does not have time at all. Stopping implies that time once flowed, like a clock ticking that suddenly halts. But photons never had a ticking clock in the first place. Time doesn't slow to zero for them. It simply isn't a dimension they participate in. Just as a two-dimensional being might never comprehend what it means to move up into a third dimension, photons don't move forward through time. Their reality bypasses it entirely. This is why physicists are careful when describing light's relationship to time. Saying time stops for light is a convenient shorthand, but it risks misunderstanding. Light doesn't freeze in a moment. It doesn't have moments at all. Its entire existence between emission and absorption is compressed into a single event. For photons, there is no in-between, no waiting, no experience of travel. They are timeless by nature. It's worth emphasizing how strange this is from our perspective. Everything we know, everything we feel, is filtered through the flow of time. Our thoughts, our actions, our lives, all of them depend on the steady ticking of moments. To imagine a reality where there are no moments is to step into a domain completely alien to us. And yet, photons remind us that such a domain exists and is woven into the fabric of the universe itself. Light doesn't just carry energy and information. It carries the proof that not all parts of the cosmos live inside time. This is also why photons make such perfect messengers of cosmic history. Because they don't age, they deliver pristine records of their origins. The light from the first stars, or from the cosmic microwave background that fills the universe, arrives untouched by the billions of years it took to cross the cosmos. Those photons haven't weathered their journey. They've simply arrived. For them, there was no journey. And so, to answer the question, does time stop for light? Not exactly. It's not that photons live in a frozen timeline. It's that time doesn't apply to them in the first place. They exist in a timeless mode of reality, moving from one point in space-time to another without experiencing the in-between. For us, bound to mass and clocks, this is nearly impossible to comprehend. But in physics, it's not just speculation. It's the logical conclusion of relativity. From our earlier explorations, we know that for massive objects, time never quite stops. It only slows down more and more as speed approaches that ultimate barrier, the speed of light. And yet, from the outside looking in, something uncanny happens. As a traveler accelerates to near-light speeds, their time dilation becomes so extreme that to an observer, it appears as though their clock is grinding almost to a halt. This creates what many call the illusion of time stopping. The key word here is illusion, because while it looks like time has frozen, it hasn't truly ended for the traveler themselves. Instead, what we're seeing is the infinite stretching of time from one perspective projected onto another. Let's unpack this. Imagine you are standing still on Earth, watching a spaceship accelerate to 99.999999% the speed of light. If you could somehow observe the crew's movements, the ticking of their clocks, the rhythm of their heartbeats, you would see everything unfolding in impossibly slow motion. A second for them might stretch into hours, days, or even years for you. Their words would draw out as though the universe itself were pulling on them. Their lives would appear to be happening at a glacial pace, and as their speed creeps closer and closer to light, this slowing becomes even more severe, approaching stillness. But here's the subtle truth. It only looks like time is stopping from your perspective. For the crew aboard the ship, nothing strange is happening at all. Their hearts beat at a normal pace. Their conversations flow normally. Their meals and dreams unfold exactly as they expect. They're living their proper time, and within their own frame of reference, the laws of physics play out without distortion. What you see as slow motion is not their reality. It's the way relativity stitches together two different perspectives on time. This distinction between how things look from the outside versus how they feel on the inside is at the heart of the illusion. To the observer, the traveler's time approaches stillness. To the traveler, time flows normally. Both are correct, because relativity says there is no single universal time. Each frame of reference carries its own truth. The illusion arises when we try to impose one truth onto another, forgetting that time itself is relative. Now, why does this illusion become so powerful near light speed? The answer lies in the way the equations of relativity work. As velocity approaches the speed of light, the factor that governs time dilation grows without bound. Mathematically, it tends toward infinity. That means, to the outside observer, the traveller's clock appears to tick infinitely slowly. Infinity, of course, is a concept we struggle to visualize, but in this context, it means that the closer you get to light speed, the longer it takes for the outside world to see even a single tick of the traveller's clock. In the limit, if you could ever reach light speed, it would take an infinite amount of outside time for even one tick to occur. From the outside, that looks indistinguishable from a frozen clock. Hence, the illusion of time stopping. This illusion has fascinating implications when we think about journeys across the cosmos. Suppose a traveller sets off for a distant star, moving at near light speed. For them, the trip might take just a few years of proper time. But for those left behind on Earth, the trip might take centuries or millennia. If we were watching them from Earth, it would seem like their time has slowed nearly to a standstill. We might even describe it as stopped, because the difference between infinite slowing and complete stillness is imperceptible from the outside. And yet, for the traveller, life continues without interruption. This is the paradoxical beauty of relativity. Both truths coexist, without contradiction. It's also worth noting that this illusion is not just theoretical. We've already observed it at small scales in particle accelerators. Muons, as we discussed earlier, live far longer when accelerated close to light speed than they do at rest. To us, their internal processes appear slowed, stretched out compared to their normal lifetimes. From their perspective, they still decay on schedule. It's the same illusion of time stopping, scaled down to subatomic particles. The same principle would apply to human-scale travelers if only we could reach those speeds. The illusion becomes even more thought-provoking when we connect it to the idea of causality. Imagine watching a photon, a particle of light, traveling across the universe. From your perspective, it may take billions of years. From the photon's perspective, as we've said, there is no time at all. To you, it looks as though its internal clock is permanently frozen. But that frozen state is not the same as experiencing stopped time. It's the absence of time altogether. The illusion of stopping is a projection of your perspective onto something that doesn't share it. This illusion also raises philosophical questions. What does it mean to say something has stopped if, from its own frame of reference, nothing unusual has occurred? Is stopping an objective fact, or is it only an interpretation made by one observer looking at another? Relativity pushes us to accept the latter. The illusion of time stopping is real from the observer's perspective, but it is not an absolute truth of the universe. It is one layer of reality, coexisting with others. To make the idea clearer, think about an old film reel. If you slow down the projection enough, each frame lingers longer on the screen, until eventually it looks like the action has frozen. But in reality, the film still contains the same sequence of frames. It's just that your viewing speed has stretched them apart. That's what happens near light speed. The traveller's timeline still exists, still unfolds normally for them. But from the outside, the frames get stretched further and further apart until the film appears paused. It's not really paused, it just looks that way. So when we ask, does time stop at the speed of light? The answer is shaped by this illusion. From the outside, yes, it looks like it does. Clocks appear frozen, processes seem suspended, journeys seem to stretch into infinity. But from the inside, no, time never stops. Life continues, moments unfold, and experience remains intact. The illusion is powerful, but it is still only an illusion, born from the relativity of time itself. We've now unraveled the illusion of time stopping, seen how photons inhabit timelessness, and traced how travelers and observers live in different truths. But when we strip away the metaphors, the thought experiments, and the illusions, what does physics itself actually say about the matter? The scientific stance is both clear and humbling. For any object with mass, time does not and cannot stop. It only approaches zero asymptotically as speed approaches the speed of light. In other words, time can shrink to an unimaginably thin sliver, but it never vanishes entirely. The mathematics of special relativity tells the story. As velocity increases, proper time accumulates more slowly for the moving object compared to a stationary observer. The closer you push toward the speed of light, the more dramatic this difference becomes. At 90% of light speed, the slowdown is noticeable. At 99.9%, it's extreme. At 99.9999999%, it's so overwhelming that seconds for the traveler could correspond to centuries or longer for someone watching from afar. But the crucial detail is this. The slowdown continues without ever reaching the final step. The curve of time's flow plunges downward, getting closer and closer to zero, but it never actually touches it. Why not? Because for anything with mass, the speed of light is not just a physical barrier, it is a boundary of definition. To cross it would require infinite energy, and the very equations of relativity break down when you attempt to insert light speed as a valid input for a massive object. The mathematics doesn't give you a frozen clock. It gives you an undefined situation. This isn't a loophole waiting for discovery. It's a signal that the concept of time stopping for mass is not just physically impossible, but logically meaningless. For light, the story is different. Photons have no mass, and because of that, they aren't bound by the same constraints. They are born into motion at light speed and exist in a state where proper time is always zero. For them, emission and absorption are the same event, stitched together across space-time with no duration in between. In that special case, the mathematics yields a clean result: timelessness. But that result applies only to massless entities like photons and, as far as we know, gravitational waves. For massive objects like you, me, or any conceivable spacecraft, the rules are unbending. Time slows, but it never stops. This distinction is why physicists are so careful in answering the question, does time stop at light speed? A strict scientific response would be, no, not for anything with mass. The equations forbid it. Time approaches zero, but it cannot reach it. What's happening at the limit is not a frozen clock, but an undefined state that lies outside the realm of physical reality for matter. To claim otherwise is to step into metaphor or imagination, not physics. And yet, this scientific stance doesn't make the phenomenon any less astonishing. The fact that time can shrink so dramatically that one person's minutes might equal another's millennia is already mind-bending. You don't need time to stop completely to realize that relativity redefines our very understanding of existence. The near vanishing of time is enough to make us question what present, future, and experience even mean. In practice, what physics really says is this: relativity is rock solid. Every experiment, from particle accelerators to cosmic rays, confirms its predictions. We can watch time dilation at work, we can measure it, and we can calculate it with extraordinary accuracy. But the exact stopping of time, that remains in the domain of photons alone. For everything else, it's a forever unreachable horizon, always just out of reach, no matter how much energy you pour into the attempt. This duality, time as an elastic, flexible phenomenon for matter, and time as non-existent for light, is one of the most profound truths modern science has revealed. It shows us that time is not a universal constant, not a stage upon which the universe plays, but a property woven into motion itself. For matter, it bends, but persists. For light, it simply doesn't exist. So, the scientific stance can be summed up in one elegant paradox. Time does not stop for the massive, but it does not exist for the massless. For us, bound to our clocks and our aging, the final state of timelessness is a frontier forever off limits. But for photons, that frontier is home. Now that we've clarified what physics actually says, that time slows towards zero, but never quite reaches it for anything with mass, it's impossible not to wonder, what if humans could somehow break the rules? What if, through some unimaginable leap in technology, or by exploiting loopholes in physics we haven't yet discovered, we managed to accelerate a human to the true speed of light? What would time feel like from that perspective? Even though science insists this scenario is impossible for us, imagining it helps us stretch our understanding of what it means to exist in time at all. To begin with, let's place ourselves in this impossible thought experiment. You're sitting in the cockpit of a futuristic spacecraft, and through some means, perhaps an exotic propulsion system or a manipulation of space-time itself, you accelerate to light speed. What happens inside your mind? What does your body feel? The strange truth is that relativity suggests you would feel absolutely nothing unusual about the transition. Just as someone moving at 99.999% of light speed experiences their heartbeat, thoughts, and inner world as perfectly normal, you too would feel as though time was flowing normally in your personal frame. But here's the catch. Your personal frame, your proper time, would collapse entirely. For you, departure and arrival would merge into the same moment. From your perspective, the entire journey, no matter how long it appeared to outside observers, would take place in zero time. This means that if you left Earth and travelled to the Andromeda Galaxy, 2.5 million light-years away, you would arrive instantly from your own point of view. You would never experience the passage of a single second along the way. There would be no boredom, no anticipation, no sense of distance. One moment you are here, the next moment you are there. For you, the universe would shrink dramatically, compressing space and time into a kind of cosmic teleportation. What appears to be an unimaginably long journey to everyone else would be a blinkless jump for you. But this instantaneous travel has a cost. Because from the outside perspective, say, people on Earth watching your journey, the passage of time would still be immense. If you travelled to Andromeda at light speed, Earth would have aged 2.5 million years by the time you arrived. Civilizations would have risen and fallen. Continents would have shifted. Stars might have been born and died. From their perspective, you would have been absent for eons, even though from your perspective you never left. The discrepancy between your timeless experience and their vast unfolding of history would be absolute. You would not be a time traveller in the sense of moving backward or forward. You would be a timeless traveller, skipping across the fabric of history in an instant, while the rest of the universe carried on without you. Now think about what this means for your subjective experience. Humans define existence through time. We think, we remember, we anticipate. If time truly vanished for us, all of those anchors would dissolve. There would be no before and no after in your awareness. You wouldn't experience the voyage. You wouldn't even experience the instant of travel. You would simply appear at the destination, as though the journey had never occurred. This raises a strange philosophical question. Would you even know that you travelled? Or would your consciousness simply register that one moment you were in one place and the next moment you were somewhere else, with no perception of having crossed the space between? For humans, this loss of duration would be so alien that it might feel less like travel and more like erasure of experience. This brings us to the unsettling possibility that if humans somehow reached light speed, subjectively, we might not experience anything at all. To experience requires the flow of time, moments stacked one after the other. Without that flow, there is no thinking, no awareness, no existence in the sense we understand it. Consciousness is built on change, and change requires time. If proper time vanished completely for us, perhaps we wouldn't feel like zipping across galaxies, but instead like nothing at all. Perhaps our existence itself would collapse, leaving no observer behind to register the event. Yet even if we set aside this possibility and assume that somehow human consciousness could survive intact, the consequences would still be staggering. The universe would look utterly different. Distances would contract down to nothing. To an observer at light speed, relativity predicts that the length of objects in the direction of travel shrinks. At the ultimate limit, this contraction would reduce the entire distance of the journey to zero. In other words, the space between origin and destination collapses. The whole cosmos would flatten along your direction of travel, compressing into a kind of infinite pancake where separation between points loses meaning. You would not only skip time, you would erase distance. But now, let's zoom back to the outside observer. From their vantage point, your clock has frozen. They would never see you complete your journey, because it would take infinite outside time for them to register your motion at light speed. They would be forever waiting for you to arrive. The illusion of time stopping we discussed earlier would, in this case, become their reality. Your existence would vanish from their world, suspended in timeless travel that never resolves. In this way, your timelessness and their infinite waiting become two sides of the same coin. This duality creates a paradoxical human story. For you, the traveler, there is no journey at all. For everyone else, the journey is endless. The question then becomes, who is right? Relativity tells us both perspectives are correct, but that truth forces us into a strange space where human notions of reality collapse. If two people can disagree not just on how long something takes, but on whether it takes time at all, then our shared understanding of existence fractures. And that fracture is what makes the thought of humans reaching light speed so disorienting. Another consequence to imagine: what would happen to your relationships with the rest of humanity? If you could travel to distant galaxies in zero subjective time, you could, in theory, leap across billions of light years in the blink of an eye. But each time you arrived somewhere, the universe outside your perspective would have aged by billions of years. By the time you returned to Earth, if you ever did, it would be unrecognizable. The people you knew would be gone, civilizations would be dust, and stars might have burned out. In this way, light-speed travel would isolate you from history itself. You wouldn't just be separated from your home, you'd be separated from your species, your era, your very context in time. You would become a permanent exile, not because you wanted to, but because time itself has erased your connection to everything you once knew. And this raises the most haunting question of all. Would living at light speed really be living? Our lives, our sense of identity, our relationships, our consciousness, everything about being human is woven into time. To exist outside of it is to exist in a way that is fundamentally incompatible with being human. If humans could somehow reach light speed, perhaps we wouldn't become eternal travelers. Perhaps we would lose the very essence of what makes us ourselves. So, what if humans could do it? If somehow the laws of physics bent to allow us into the realm of light, the result would not be the exhilarating adventure science fiction often paints. It would be something far stranger, far more alien. To us, it might not feel like travel at all. It might feel like erasure. Time and space would collapse, awareness might vanish, and our connections to everything we know would dissolve in an instant. For light, this state is natural. For us, it may be uninhabitable. We've traced the scientific arc of relativity, the energy barrier, time dilation, photons, and even imagined what it would mean if humans somehow reached the speed of light. But now it's time to step outside the mathematics for a moment and wrestle with a deeper question. Is time something that can stop at all, or is time merely a measurement humans invented, an illusion of perception rather than a fundamental entity? This philosophical twist doesn't undermine the science. Instead, it pushes us to confront the assumptions behind the question itself. From the beginning, our everyday experience tempts us to think of time as a flowing river. Seconds pass, minutes accumulate, hours roll forward, and days stretch into years. The ticking of clocks and the aging of bodies seem to prove that time is a real, independent thing, moving forward whether we notice it or not. But physics and philosophy have long debated whether time is truly an entity out there in the universe, or whether it is a construct in our minds, a way of organizing change into a narrative we can comprehend. Einstein himself hinted at this deeper mystery. In his theory of relativity, time is not a universal flow, but a dimension woven into space-time, changing with motion and gravity. Events don't exist in some single now, experienced by everyone equally. They exist as coordinates in a four-dimensional fabric. From this perspective, time doesn't really flow at all. Past, present, and future all coexist as different slices of space-time, and what we call now is just the slice our consciousness happens to occupy. If that's true, then asking whether time can stop is a little like asking whether space can stop. It assumes motion where there may only be structure. This brings us to the first philosophical possibility. Perhaps time is not a river, but an illusion of perspective. What we feel as time flowing might just be the brain stitching together moments of perception, like frames in a movie reel. Our experience of duration may be less about the universe and more about how consciousness processes change. If that's the case, then asking if time stops at light speed is like asking if the movie projector can run out of film. For photons, there are no frames, no narrative, just timeless existence. For us, the projector never halts as long as consciousness persists. The very question might reflect our human limitation, not a fundamental feature of reality. Another perspective comes from philosophy of physics. Time may be nothing more than a measurement of change. When we say time passes, what we really mean is that things change. Clocks tick, planets orbit, atoms vibrate. Time is a label we attach to the ordering of those changes. If no change occurred anywhere in the universe, would time exist? Or would it vanish into irrelevance? If time is merely a measure of change, then it doesn't stop at light speed. It simply becomes irrelevant for entities like photons, whose states don't change in the way matter's states do. For them, there's no diary to keep, no events to order, and therefore no need for time. But there's a deeper paradox. If time is just a human measurement, then so is the very question we've been asking. The idea that time slows or stops may itself be a reflection of how we measure, not an intrinsic property of the universe. The equations of relativity don't talk about time stopping in the way we imagine. They describe how proper time along a world line becomes zero for light. That's not stopping so much as redefining. Photons exist outside the human category of time altogether. Our language bends here, struggling to keep pace with reality. Consider also the possibility that time is emergent, not fundamental. Some physicists speculate that time arises from deeper laws of quantum mechanics or thermodynamics. In that view, time is a statistical property of the universe, emerging from entropy, the tendency of systems to move from order to disorder. If time is emergent, then perhaps it doesn't exist in the same way energy or mass does. Instead, it's a convenient bookkeeping tool, useful for describing how systems evolve, but not an ingredient of the cosmos itself. If that's true, then asking whether time can stop at light speed may be like asking whether temperature can stop at absolute zero. It's not a matter of halting something real, it's a matter of a measurement losing its meaning. There's also the haunting possibility raised by philosophers. What if time doesn't exist at all? Some schools of thought argue that time is entirely an illusion, a human construct with no objective reality. Julian Barber, a physicist and philosopher, famously argued that what exists are nows, individual configurations of the universe frozen in timelessness. Our experience of flow is just the brain linking these configurations into a sequence. In that framework, the photon's timelessness is not strange. It's just a more honest reflection of the true nature of reality, one that we usually disguise with our perception of flow. If time doesn't exist fundamentally, then photons aren't exceptions. They're simply revealing what has always been true. So where does this leave us? Science says time slows for matter as it nears light speed and vanishes for photons. Philosophy says we may be misunderstanding what time even is. Is it a river that can stop flowing, or a coordinate that never flowed in the first place? Is it a human measurement of change, or a fundamental property of the cosmos? These questions don't have final answers, but they reshape how we think about the mystery. Perhaps the most honest conclusion is this: when we say time stops at the speed of light, what we're really doing is testing the limits of our language. We're trying to describe something that sits at the boundary between human experience and cosmic truth. For matter, time slows to near zero. For light, time is not even part of the equation. For us, bound to clocks and memory, this feels like stopping. But the universe may not see it that way at all. In the end, the philosophical twist is this: maybe time cannot stop because it never flows. Maybe time isn't a thing in itself, but a shadow cast by motion, change, and perception. And maybe the timelessness of light is not an exotic exception, but a reminder that reality itself is far stranger than our human categories can ever contain. After all the explorations, the laws of relativity, the strange behaviors of near-light particles, the illusions seen by observers, the timelessness of photons, and even the unsettling philosophical twist, we arrive at the point where science, imagination, and awe collide. The question of whether time stops at the speed of light is not just about equations or experiments. It is about confronting the limits of human understanding. Time is so deeply woven into our identity, our perception, and our language that imagining its disappearance feels almost impossible. And yet, the universe insists that beyond the barrier of light speed lies a reality where time, as we know it, is absent. For us, bound by mass and matter, time will never truly stop. No amount of energy, no feat of engineering, no future technology will let us erase our proper time. We may approach the limit asymptotically, stretching our seconds into near eternity compared to the outside world, but the last step is barred. It is not a frontier to be conquered. It is a wall that defines who and what we are. To exist with mass is to exist with time. Our lives are written in its flow, and to remove it would be to erase the possibility of human experience itself. But light plays by different rules. For photons, proper time is not slowed, it is non-existent. They move through the cosmos outside the stream of duration, carrying messages across billions of years without ever aging, without ever waiting. They are timeless couriers of the universe, proving that time is not universal, but relative, not absolute, but conditional. In their existence, we glimpse a domain that we can describe mathematically, but never inhabit ourselves. And this is where the mystery deepens. What does it mean that something as fundamental as light does not share our reality of time? Is time truly a feature of the universe, or is it a feature of us, creatures of mass and memory? Does the timelessness of photons hint at a deeper truth about the cosmos, one in which time itself is secondary, emergent, or even illusory? These are not questions physics has fully answered. They linger at the edges of science, in the space where equations meet philosophy and where curiosity becomes wonder. The most dramatic realization is that the question, does time stop at light speed, might itself be the wrong kind of question. For us, it cannot stop. For light, it never began. The phrase time stopping is really a translation, a way of trying to compress an alien truth into human language. What's actually happening is something stranger. The very framework of time dissolves at light speed, replaced by a mode of existence that lies beyond our comprehension. And that's what makes the question so endlessly captivating. It is not just a puzzle of physics, but a mirror held up to our minds. It forces us to realize how much of what we take for granted, seconds, minutes, days, the steady beat of time, is not universal. It reminds us that our experience is local, relative, and deeply tied to the limitations of mass and motion. Beyond those limits, reality transforms into something we can only describe in equations and metaphors, never in lived experience. So we end where we began, with the haunting mystery that started it all. If you could travel at the speed of light, would time really stop for you? The answer is both yes and no. And more than that, something stranger still. For you, with mass, the answer is no. You can never stop your own time, never escape its flow. For light, the answer is not that time stops, but that it does not exist. Time is irrelevant in the realm of photons, as foreign to them as timelessness is to us. And so the dramatic takeaway stands as both a conclusion and a beginning. At the speed of light, time as we know it ceases to exist, not for us, but for light itself. And that's why the question of time stopping remains one of the deepest mysteries in physics. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.